I'm Adam Anders, manager of the Power Platforms team here at Wolfspeed. Today I'm going to show you how to use the SpeedVal kit to perform system testing running it as either a buck or boost converter. You can run either synchronous or asynchronous configurations with this setup. The main pieces that we have here are the motherboard, the gate driver card, the power card, and the buck boost board. When we configure all these together, we can set it up as either a buck or boost converter, just depending on how you wire to this buck and boost filter board. So I'll show you how to make those connections, and then we can move into the testing. So to get things set up, we're going to take the buck boost board. I'm going to line up the holes along this edge, which have plated pads on the bottom, with the screw terminals on the motherboard. You can line that up and then connect the two boards together with these 5 screws, and then everything's good to go. We've now connected the switch node on the motherboard to the inductor and the filter caps on the buck boost board. So after you get the screws in to connect the two boards together, next thing you're going to want to do is plug in the voltage feedback cable. This is necessary if you're using the control card. It allows the controller to monitor the voltage on the capacitor bank on the buck boost filter board. The other thing is plugging in the fan. This is here just to help keep the inductor cool while you're running under high power. So the next thing we're going to do is make the high current connections for both the source and the load. So this is where you can make the decision whether you want to run it as a buck or boost, just depending on how you make those connections. So today I'm going to show running it as a boost converter, but you can consult the user guide for the configuration for running it as a buck converter. So I'm going to hook up the load to the plus and minus bus, and the source then goes between the input-output node and the minus bus. So now that these are on there, we can tighten down the screws, and then we can move on to hooking up the scope probes so that we're ready to run. So let's talk a little bit about the equipment that you're going to need for this test. So we have a high voltage, high current DC source, a DC electronic load, and then a power analyzer so that we can perform efficiency measurements on our setup here. We have a safety enclosure so that when we're running it, we can close it and keep everything safe for the user. Inside here, we have a load resistor. So in addition to the electronic load, it's always a good idea to have a light passive load there that's always present, especially when you're running an open loop boost configuration. That can help keep the bus voltage from pumping up beyond where you want it to. Next, we've got a thermal camera that we're going to use to look at the devices, the MOSFETs or diodes, as we're testing it, and take some thermal measurements of the case. And lastly, the scope so that we can take a look at the currents and voltages while the equipment is running. So the next step is to plug in our probes to the power daughter card. So we've got a high voltage probe to measure the drain to source voltage. We've got a gate to source voltage measurement using a 10x probe, and then also a current shunt for measuring the drain current of the lower switch. You can also measure the upper gate and drain voltages, but be mindful if you're doing that, you need to use an isolated probe. Something such as the IsoView probe from Tektronix works very well for that, but you want to make sure not to connect any passive probes to that upper device during testing. So I'm going to plug that into the motherboard here, lock it in place. I've already got the gate driver configured, and the 2 PWM signals. In this case, I'm running a synchronous boost, so we're driving both the upper and the lower switch. So I've got those coming in, being fed from a function generator. And I've set the jumpers on the board to use that external BNC input for the PWMs rather than the control card input. So we're almost ready to start power testing. You want to make sure that if you're operating without the controller, that you flip the switch on the motherboard to turn on the fans. Make sure that those are running and you're going to be cooling the devices and the inductor. Get your thermal camera all set up, and then we're going to start bringing up power very slowly. So you're going to want to start with a low voltage, low power draw, and just slowly build your way up to your desired power level. It's always a good idea just for safety, make sure everything's functioning properly before you get too carried away at those high power levels. So since we're running a boost converter today, the lower switch position is going to experience switching losses and conduction losses, whereas the upper device is really only going to experience conduction loss because the body diode is going to take over during the dead time, and you're not going to have that turn on and turn off switching loss in the MOSFET. So when we look at the temperatures later, we're going to see a difference in temperature between the two devices, and that's why. So this topology you can use to evaluate switching behavior for both soft switched or hard switched, depending on which device you want to look at during the test. So I'm going to start by bringing up the voltage slowly and verifying here that the output voltage is twice the input voltage, because in this case I'm running at about a 50% duty cycle. So with the boost converter, I'd expect that input to output ratio to be about 2 to 1. So everything looks okay here. I'm going to continue to ramp that voltage up and then slowly continue ramping the voltage up to my desired set point. Okay, so now I've gotten to 200 volts input, 400 volts output. Now I'm going to slowly increase the load. I'm going to continue to ramp the power up. It's a good idea to keep an eye on your thermal measurements at this time. I'm going to continue to ramp it up to about 4 kilowatts, and that's going to be our steady state operating point. Once you get to that point, let the system sit until the efficiencies and thermal measurements stabilize. You can take your readings there and then move on to a different operating point, change your gate resistor, change your MOSFET, do whatever you need to do with the kit to reconfigure and test all the different parameters you want to explore. So we finished our thermal run here, took all of our efficiency measurements, thermal measurements, looked at the scope results, very happy with everything here. So now you can reconfigure the board with a different MOSFET, different gate driver, test other operating points. There's just all sorts of different things you can do with the SpeedVal kit. Now you know how to use the SpeedVal kit to perform high power measurements in your own lab. For more information, contact your Wolfspeed representative or visit wolfspeed.com/SpeedValKit.